Dr. Ravishankar is with the Department of Physics since 1989. He obtained his doctor's degree from the University of Mysore in 1987 and subsequently carried out postdoctoral research as a visiting fellow at TIFR, Mumbai. He is a theoretical physicist whose chief interests are quantum chromodynamics with emphasis on quark, gluon, plasma, quantum information theory, and quantum Hall effects. Apart from core courses, he has taught several electives in high-tech research areas such as special and general relativity, particle physics, quantum chromodynamics, and quantum computations. I give you Dr. Ravishankar.
So, okay, Apurva was speaking of very deep aspects of life, so he is entitled to exceed his time. And there is one phrase which I have been hearing very often in this talk. Product phase space, it is always represented by a point in the phase space again, the bigger phase space. Therefore, if I were to start with a big system and start going to smaller subsystems by tracing over the unwanted degrees of freedom, the system will continue to remain pure, will continue to remain separable, or it will be pure, sorry. But on the other hand, if you are going to look at quantum mechanics, my Hilbert space is much, much bigger than the classical phase space. That is the lesson that we learned from quantum mechanics. Unfortunately, for 50 years or 60 years, we did not emphasize that. What we emphasized was uncertainty principle, principle of indeterminacy, so on and so forth. And one good thing that quantum information theory has done is to emphasize this, that there is a lot of space, large number of states which are available. In fact, there is a large number of copies of the phase space which are sitting in the Hilbert space. And many of them cannot be reduced to points in the phase space, and these are your classic Bell states, up, down, minus, down, up, down, plus, down, up, so on and so forth. And in writing this, I am emphasizing the spin notation, using the spin notation. If you are in information theory, you would of course employ the notation 0, 1, 1, 0. Okay. Of course, these Bell states are not just 4 in number. There is a local transformation you can perform on any one of them, SU2 cross SU2, okay? There is a large set of them given by a continuous family. So now what we want to do is to quantify entanglement. These are what are called as the completely entangled states. Because if I say that I am not interested in the spin of one of the electrons or one of the qubits, let us say, I simultaneously lose my information about the other spin also, it becomes a uniform distribution. So the corresponding classical statement is that if I sum over the information contained in one of the spins here, and if I looked at the distribution, that would be a uniform distribution on the sphere, because classically a spin is nothing but a vector of a fixed length, and it can move anywhere on the sphere. So how do we quantify the partial entanglement? The partial entanglement is very easily quantified by simply asking how much it is separable and how much it is not separable. So let us not get into that. What we shall now do is to look at a bigger class of states, namely my system is not pure, but actually it is sitting in a mixed state. So in a mixed state, what I have is not a coherent superposition of pure states, but I have an incoherent superposition of pure states. In fact, an extraordinarily important class of incoherent superposition of superposition of states was shown by Anil Kumar. He produced what are called as the pseudo-pure states. In fact, I will have to say something about that at a later time. Okay. Now when I am looking at the incoherent superposition of pure states, part of it is classical. The weights that I associate with these states, they are probabilistic rules. But within each state, there are lots of quantum correlations. Therefore, if I am going to look at a mixed state, there is some kind of a mix-up, an entanglement of classical information and quantum information. Now, the question is, how much of the information is classical, how much of the information is quantum mechanical, and how do I separate them? Question that we have. In other words, how do I disentangle, how do I separate the classical correlation from the genuine quantum mechanical correlation? For example, the Bose-Einstein condensates, of which we have heard so much, the cold atoms, right? There they have been able to prepare atoms, 3,000 of them. They are sitting at nano Kelvin. All of them are. So the limitation in quantum mechanics is not that of size, but how coherent it can be. People have been able to see interference, so on and so forth. So what we are now going to look at is the mixed 2-qubit states, the simplest of the states. Now, when it comes to mixed 2-qubit states, you know, being a high-energy physicist, we always dream of explaining all the laws of physics with a single Lagrangian. We should not probably exceed 2 lines, like string action, let us say. In a similar manner, one would like to have a minimal number of parameters that describe the nature of entanglement in the mixed state. And the so far has been to describe it by one number. Just as the entanglement of a pure state is described by one number. If it is 0, it's a separable state. If it is partially separable, then it takes any value between 0 and 1. And if it is 1, of course, it is a fully separable state. And one way is actually to look at the entropy of the reduced density matrix and normalize it to 1. That is a good measure of entanglement. Now, when it comes to entanglement of the mixed states, people have given many, many criteria, depending on what they consider to be an important quantum feature. And one very, very popular, very famous criterion is the so-called concurrence. So in concurrence, what you do is to ask, in how many ways could I have prepared the system? Now, if I could prepare the system by incoherent superposition of classical states, separable states, I say that there is no entanglement. That is a nice criterion. This is called the entanglement of formation. However, at this point, I would like to comment that although the idea is very interesting, in quantum mechanics, we cannot ask the question how a system was prepared. For example, let me look at unpolarized light, which we are all familiar with. Well, Professor Anil Kumar will give me an unpolarized light beam. I cannot go and assert whether he prepared it by superposing two equal admixture of circularly polarized light, or elliptic polarized light, or plane polarized light. That information is gone. However, if you imagine this in terms of the cost, how much effort is it required to prepare a state, this is quite a useful notion. This notion is not completely operational because we don't know how to find it out, how to measure that. But for two spin-half systems and a spin-half spin-1 system, there's a criterion. Okay, what you do is to take this what is called as rho transpose by operating them through sigma matrices, and then you calculate this quantity R, and then you measure, give this measure. So what you do is to try to characterize the entanglement contained in a mixed state through this C. This is what is called as the concurrence. Now, an equally interesting measure is what is called as the negativity, which was introduced by Werner. Here you ask, how did I prepare the system again? So what I prepare the system is, take a state belonging to this system, take a state belonging to this system, put them together. Then take another state belonging to this system, another state belonging to this system, put them together. Associate classical weights. Now, if my state can be written in that particular form, could have been constructed in that particular form, I will again say, look here, separable states are classical. I have incoherent superpositions of such separable states with positive weights. Again, say that there is no entanglement contained in it. This definition is again, unfortunately, not completely operational. Because of great efforts of Perez and Horodeczki, we have a criterion called negativity. What you do is to write the density operator in a separable basis, do a partial transpose, and look at eigenvalues. If the eigenvalues, if at least one of the eigenvalues is negative, then that's an indication of the entanglement. So the point that I am trying to emphasize is that the notion of entanglement is not unique. It is not straightforward. All definitions of entanglement of a pure state are equivalent to each other. They are all relative monotones. All that I do is to do a little bit of dilatation, I twist it here, twist it there. But there is a nice one-to-one onto mapping. They are relative monotones, but these are not. So probably we should ask which one of them is robust, which one of them is better, or is it possible that these two are merely benchmarks, and what we need is a slightly more comprehensive discussion, more comprehensive description of what the entanglement is. And that is the attempt which Shantanu and I did, and I would like to sort of present that result. And before I go ahead, probably it is nice to look at these figures where we have plotted concurrence against negativity, and you see that there is quite a good spread. There are some results which are known. For example, concurrence is always an upper bound on negativity. But that doesn't mitigate matters very much, because there are states with zero negativity and non-zero concurrence, and no, depending on your taste or prejudice or whatever, you will say the system is entangled or the system is not entangled. So perhaps we should go beyond these kind of benchmarks. Of course, these benchmarks are all quite useful, okay? We would like to understand these benchmarks in terms of a more general discussion, and let us see how we can do that. Now there is yet another motivation which I got actually from his talk in Kanpur Symposium, Anil Kumar's talk, and that is, irrespective of what we theorists say, physicists say, what is entangled and what is not entangled, experimentalists have gone ahead and built NMR quantum computers. They are jolly well doing quantum computation. They were able to create gates, and yesterday we learned they are able to even play games, quantum games. Now you see, when I say that I am able to do gate operations, so I am going to use a Hadamard operator, I am going to build a Trifoli gate, I cannot imagine doing any such thing with a classical system. That is quite impossible. Is that okay? So the question is not which of them is a better definition. Actually the question is, how do we actually unravel the entanglement content which is contained in these pseudo-pure states? Now take the definition of any of the definitions that you want, negativity, concurrence, whatever, they will all tell you that there is a number of states around the origin, the completely unpolarized state, all of which have zero entanglement. And yesterday he was emphasizing that the weightage associated with the pure state is 1 in a million, 10 to the power of minus 5, and be assured that all of them have zero entanglement according to these benchmarks. And we have our experimentalist colleagues who are actually doing quantum computation. So we would also like to understand how to really describe these particular systems. I think people have been able to go all the way up to 12 gates or whatever. Okay. The basic idea is actually what happens in a classical system when I look at a system in the phase space. How do I represent a system in the phase space? I represent it by a point in the phase space. And it has sharp values. We have no uncertainty principle. It has a momentum, fixed position, fixed energy, fixed angular momentum, so on and so forth. Then what do? I say, no, my system is not in a pure state. My system is actually an ensemble of pure states. That is what a statistical description is. Then what is a point in the phase space? A Dirac delta, it becomes mirrored, it becomes a distribution function. A distribution in the mathematical sense becomes a well-defined function, a distribution function. And now we know the minute we do that, all observables acquire a statistical character. I cannot ask questions like, give me the momentum of a gas at a temperature 200 Kelvin. I cannot ask what is the energy. I can give you mean energy, I can give you RMS, I can give you fluctuations and so forth. In a similar manner, as this cartoon shows, if I imagine that there is a mixed state, I should remember that what it is representing is not a single quantum state, but an ensemble of quantum states. That is, in fact, indeed, the philosophy behind NMR computation, the bulk computation or the ensemble computation. Now, whenever I am looking at the ensemble, there are any number of microstates. Of course, if all the microsystems are in the same microstate, you have simply taken a direct product of that many states. You can imagine that to be the pure state. Otherwise, you have a distribution of that particular kind. Therefore, it is very difficult to motivate ourselves to say that entanglement should be described by distribution. Why am I looking for a value? I should actually ask how the entanglement is distributed. So, just as we go from a Dirac delta distribution to a good distribution function, we would like to do the same thing even in the case of entanglement. Of course, we have to use a certain number of criteria in order to meaningfully define that. So, let us see how to go about doing that. So yesterday when KRP was showing me his book, he introduced a very interesting notation. Rho was called elementary quantum resource, is that right? The density operator, and the pi's were called events. So I was pretty happy to see that, because what we are going to do is to write my density matrix in a very peculiar fashion, but I'll tell you why it is being done. So I have my density operator. It is a 4x4 density operator for all our purposes, all practical purposes. It is characterized by 4 eigenvalues, non-negative eigenvalues. They will all add to 1, and there are 4 eigenstates given by psi I. This is the Hermitian operator. Now it has a natural resolution, lambda I, psi I, psi I. But what I want to do is to write it as a hierarchical sum. So what is the hierarchical sum that I want to write? So first of all, what I will do is arrange the eigenvalues in the non-increasing order. Lambda 1, sorry, that has got missed out here. Greater than, oh, it is written there, non-increasing order. So I look at the difference and I write it as a one-dimensional projection. So that one-dimensional projection, if you want, is the eigenstate belonging to lambda 1. Then I look at the difference between the second and the third eigenvalue. I write it as a two-dimensional projection. That two-dimensional projection is nothing but the sum of the eigenstates, incoherent sum of psi 1 and psi 2, belonging to lambda 1, lambda 2, so on and so forth. And this is a trivial identity. Is that part okay? Because whether you write it as lambda I, psi I, or you write this, it's a trivial identity. And we can see that there is a hierarchic information content about the purity of the system, if you feel like. So if I were to write a vector, lambda 1 minus lambda 2 minus lambda 3 minus lambda 4, and lambda 4, the first non-zero entry will give me the minimum dimension of the space in which the subspace of the Hilbert space in which the system is sitting. And in fact, the norm of that vector is a very simple measure of the purity of the state. That is what we want to do. The last projection, pi 4, is a universal projection because there is the full Hilbert space. Okay? So that is common to all the systems. Therefore, what we have is a hierarchy. Therefore, what we want to do is stated in a very simple way. I would like to associate entanglement not only with pi 1, that is the pure state. What is the entanglement distribution in the two-dimensional space, three-dimensional space, and the four-dimensional space? Suitably weight them, add them up, and I want to create a nice entanglement distribution of the states in the whole Hilbert space. Now, this is a sort of climb down because when people are giving me pretty numbers, I am trying to create a distribution, but as we shall see, it is not that particularly bad. Each of them comes with very beautiful morphological or topological features, not topological in the sense of mathematics, but in the sense like yesterday engineers were telling us, where points where there is a intersection, etc., discontinuity, singularity, etc. And when I take this sum, we will see that that memory is not obliterated. That state can almost be reconstructed. So in the next few of the slides, what I will try to do is to describe the procedure. The procedure is very simple. So let me imagine that my density operator was a projection operator. What is the meaning of the statement that the density operator is a projection? Let us say two-dimensional projection. That means all the states in the two-dimensional projection have the same probability. Because if I calculate the expectation value of that psi in that row, I will get 1. Because rho by definition is nothing but realizing that particular projection. So if I were to use a simple statistical language, let me find out the probability density for an entanglement for any given state in that particular subspace. That is a question that I will ask. Well, all that I need to know is the Haar measure for the states as I span over that set. Then I have the delta function and then I integrate over that. That will give me a measure. I divide it by the volume of the space which is given by the Haar measure, and that will give me a probability density. As simple as that. So this is a prescription which we want to implement for all the dimensions. Is that okay? 1 dimension, 2 dimension, 3 dimensions, and 4 dimensions. This is a perfectly operational procedure. You don't have 2 qubits, you have 2 qubits, 2 spin 3 by 2, or you have 2 spin 1, or for that matter a spin 1 and a spin 10, you can exactly use this. Only a resolution in terms of the projections will change, my original density matrix, and we would like to see what the distribution is. Once we have given this distribution, we have not implemented the most general bipartite state. We have concentrated only on the 2 qubit mixed state because all known quantum computers, whether they are based on quantum dots or NMR or superconducting bits or even quantum Hall systems, they employ spin half or pseudo states or optical. So that is what we would like to characterize. So what we shall do is to start with the simplest case, pi 1, one-dimensional projection operator. So this is nothing but the delta function with a weight given by 1. All the other states have 0 probability. Okay. Now, I come to the 2-dimensional case. Actually, I should have discussed maybe the 4-dimensional case because that is the other simplest case. It's a universal case, but anyway. 2-dimensional case is actually the most interesting and the richest. It was quite complicated for us to analyze that. So I have a linear superposition of 2 possible states which span the complete state. So the Haar measure is simply given by SU2. That is what we have. The space is essentially SU2. So what we want to do is to analyze the nature of the probability distribution. But then I know my entanglement is unaffected by local transformations. I can perform local SU2 on one spin. I can perform another local SU2 on one spin. Therefore, I freely use local transformation to characterize that. So there are some small technical details. I can always choose a basis such that one of them is purely separable. Give me a linear combination of two possible states. I can always make one of them in the span. In the span of the space, I can always make one of them purely separable. The other basis state can be chosen to be orthogonal to that. I have a lot of freedom in SU2 cross SU2. There are 6 parameters, right? I employ them to choose all of x, y, and z to be non-negative numbers. So now you see, the full space is characterized by essentially two numbers, x and y. Because z is given by root of 1 minus x squared minus y squared. Therefore, my entanglement distribution as a functional defined over this should be characterized by a minimum number of maximum two parameters. So we are not going to try to understand in terms of one single parameter. That is the picture. Now here is some technical detail. So what you do is, okay, let me explain the figure first. This is a generic figure curve for the distribution of the entanglement that we find. This is a probability distribution curve. Now, the topological features that I was speaking of is here. There is a point of maximum entanglement at which it becomes a step function. It falls and it goes to 0. This is a universal feature. This I will call as Emax. And here is a point of the cusp. This picture does not show the nature of the cusp. Actually, it is a divergent quantity. At that point, the probability density is diverging. It is diverging logarithmically. You can see that analytically. So this I will call as the E cusp. Now, if you did a little bit of analysis, you will find like a Gaussian is characterized by the peak value and the variance width. That is all what I need. This curve, although its analytic form is pretty complicated. In fact, both the left-hand side and the right-hand side of the curve are some elliptic functions. Never mind about that. The curve is completely characterized by giving, for example, E cusp and E max. Well, you can't give me E max, never mind. You can give me the E max and the probability density at E max. If you give me that, this whole curve can be reconstructed because my parameters x and y, which characterize the space, also gets reconstructed. Okay. So now we see that therefore the complete information on a two-dimensional entanglement is contained in two parameters. These, let us say E max and probability of E max, or E cusp and E max. So at this point, it is good to take a digression and ask ourselves, what is concurrence for these objects? Remember, the motivation for concurrence was you wanted to find that particular decomposition of states which gives me minimum entanglement. That is the entanglement of formation. Now look at these curves. Here is one curve, the red curve, and another is the blue curve. Purely in terms of population, probability, the blue curve has many more entangled states than the red curve. So, naively speaking, I would have expected the concurrence for the blue curve to be larger than that of the red curve. Nothing like that. We can derive an analytic expression for concurrence, and what we find is that the concurrence is sensitive to the difference between the E cusp and the E max. It looks for the difference between the point at which the maximum entanglement occurs and the point at which the cusp occurs. Now suppose E max were the same as E cusp. That is the blue curve that we have shown, which has a very large population of entangled states. That is, if I were to try to put an analog of a polarizer, I have an unpolarized light, let us say, and I put a polarizer, I get 50% of circularly polarized light. But if I have 100%, I should get 100% red polarized light. So imagine red polarized, right circular polarized light. So if I imagine, for example, entanglement is the analog of right circular polarization, by some filtration process I should be getting many more entangled states, but concurrence tells us no, it is 0 because E max is the same as E cusp. Therefore we see it is some kind of a benchmark, although it has a very strong intuitive foundation for its definition. The way it gets realized as a distribution is rather peculiar. Okay. I can also imagine the situation where this cusp actually moves to 0. There is maximum number of states are having 0 entanglement, in which case you will find that the concurrence is simply given by half of E max. the maximum concurrence that a two-dimensional distribution can take is simply half the maximum value. So you see all pi2 have a concurrence less than half. This is a sort of non-intuitive result, unexpected result, and probably one should go back and ask ourselves what really people mean by giving such kind of definitions which are motivated by vague classical quantum analogs, which is a rather complicated thing. These curves are also characterized by certain scaling results. These are of technical interest, so let me not get into that. So let me proceed to the three-dimensional subspace. Now in a three-dimensional subspace, I have a projection operator. So I would like to repeat, except that now my space over which I have to average, the group operation is by SU3. So I need a Haar measure for SU3. Luckily people have constructed Haar measures for SU3, SU4 in terms of Euler angle resolution like things. So we repeat the same analysis. We take the full liberty to do all possible local transformations, SU2 cross SU2 transformations, to describe the entanglement distribution in its simplest form, in its canonical form. And the simplest thing that you can see is that you have of the basis which are 3 in number, you can always choose them, 2 of them to be separable. In fact, they are orthogonal, therefore they can be chosen to be up, up and down, down. And the third state will be a linear combination of up, down and down, up. So once we employ this particular basis, we will ask what is the entanglement. Now, it is a good question to ask, to pause ourselves and ask, how many parameters will the entanglement of a three-dimensional distribution be characterized by? Mind you, I want to give a locally invariant description, but then all three-dimensional spaces are equivalent to what? Equivalently characterized by its dual, the vector which is orthogonal to that. In a four-dimensional subspace, either you give me the three-dimensional subspace or the one-dimensional space which is orthogonal to that. And the only locally invariant information that is contained in the one-dimensional subspace, that is a pure state, is its entanglement. Entanglement is invariant under local operations. Therefore, the probability of the entanglement is characterized by exactly one parameter. And what is that? That is the entanglement of the orthogonal state. So that is what we have written at this particular point. So what we would like to see is how the distribution behaves as a function of the E perpendicular. That is what we have plotted. Again, remarkably, the curves may be very complicated. It is not too complicated. All the distribution function can be collapsed into this particular form. E perpendicular is larger of E and E perpendicular because I am plotting it of E and this is the probability. There is a very beautiful topological property that the derivative is discontinuous at E equal to E perpendicular. So if I were to ask, or if an experimentalist were to ask me, tell me, I know that my distribution is a three-dimensional subspace, the density matrix, I want to characterize the curve, I would say don't try to reconstruct the whole probability distribution, look for the point at which the derivative is continuous. So you give me E perpendicular, I know the state uniquely, the perpendicular state up to SU2 cross SU2 transformation. That determines the three-dimensional subspace, and therefore that determines the three-dimensional probability distribution, and that has this universal behavior. So it is quite remarkable that my entanglement is showing up as points of singularities and discontinuity. One-dimensional projection, unbelievably singular, delta function. Two-dimensional projection, there is a step function, and there is a cusp where the probability density is blowing up. Three-dimensional distribution, the functions are continuous, but they are not as smooth as we would like them to be, because the derivative is discontinuous. The derivative is a step function. So these are the markers, or the morphological features that I was speaking of. So you keep counting them. There will be a finite number, not too large a number, and that will characterize the complete entanglement property of the two-dimensional mixed state. Okay, I have to keep up my promise. I am looking at my watch. The entire Hilbert space, if I look, which is the universal background, like the noise that we have, what you get is this curve, which was generated by numerically. There are many other people who have actually asked what is the probability for a state to be entangled. There are many equivalent, not entirely equivalent distributions. Now here you see, this is a perfectly smooth curve, which is going all the way from 0 to 1. No discontinuity, no singularity, nothing. Is that okay? So smoothness is uninteresting and unimportant in quantum entanglement, at least as quantum information theory as far as we see. So far we have been able to describe individual projections Now I have to go back and ask what is the entanglement content in the full density matrix, for the full density matrix, and that is where I employ this resolution. I had already given that. So what we do is to rescale slightly. I will divide all the classical weights by the largest eigenvalue, and I will write my probability distribution for a given entanglement is the probability distribution for that particular subspace, weighted by this factor, the non-negative vector, and then you have, of course, the last one, the lambda 4. Now, we can see that we are actually superposing states of different types of discontinuity or singularity, and these are continuous parameters, therefore that information will not be lost. So even in the superposition, I will be able to sort of reconstruct, recover the information coming from the states, and this is a typical curve, like the kind of snowman or whatever the children make with snow. So this is the information coming from the one-dimensional distribution, and here you can see this is coming from the three-dimensional part, the E perpendicular. Here is your cusp, and here is the point at which my two-dimensional distribution dropped to 0, E max. So I can subtract the background, and then I can look at the two-dimensional distribution. One can essentially reconstruct the probabilities. Okay, the individual curves. Now let me pause for a minute and ask how many parameters do I have? So I have 3 eigenvalues. The 4th eigenvalue is not independent because trace rho equal to 1. So that is 3 in number. The entanglement of a pure state is 1, that is 4. Two-dimensional distribution has 2 parameters, that is 6. Three-dimensional distribution has 1 parameter, 7. So what we are saying is that a proper description of the entanglement property of a 2-qubit mixed state is in terms of 7 parameters and not in terms of just one single number. Now, in order to illustrate that, what I will do is to look at a 3-dimensional curve. Okay. Yeah. Now, if you look at 3-dimensional distribution functions, let me look at this 3-dimensional distribution function. This E perpendicular can lie anywhere. Suppose E perpendicular equal to 1, I would get a straight line for the distribution. If E perpendicular were equal to 0, that would be some kind of a logarithmic, that Cauchy inverse function. And it is a mathematical theorem that the concurrence for any 3-dimensional subspace projection is identically equal to 0. So benchmarks like concurrence and negativity are unable to distinguish the rich difference in these particular states. Okay? They are just unable, but we see that our description is actually characterizing it properly by this E perpendicular. Therefore, we can give it an associated weight, and probably these can be used as resources for the entanglement. Okay. Now I come to the most important physical example that we are deeply interested in. So to us, actually the whole controversy about whether quantum entanglement is required in quantum computation or not is a redundant, sort of a wasted question, because people have been trying to settle these questions by looking not at proper entanglement distribution, but at benchmarks. And you know, benchmarks sometimes succeed and benchmarks sometimes fail. But in our description, we have no problem because we have a universal background, that is the 4-dimensional space. And what do people do in quantum NMR quantum computation? They apply unitary operators. Now under unitary transformation, my completely mixed state, identity operator goes to identity operator, nothing much can be done. But a unitary transformation can change the entanglement of a state. It can allow you to make gates, etc., etc. Therefore, the weights associated with the pure state automatically give you the entanglement, which is what they called as the deviation density matrix of the pure state. It emerges very naturally. So, you know, it is like, since I come from an Institute of Technology, it is like saying that most of the students don't qualify, therefore nobody qualifies. That is incorrect. We are actually looking at the tail of the distribution when we want to admit 2,000 or 3,000 students out of 3,000 students. This is exactly what NMR does. Most of them are unpolarized, but it looks for the cream, which is actually having a polarization. And we should be able to recover such a description, and that comes without any extra cost. Without any extra effort, the definition is inbuilt into it because they have naturally non-zero entanglement. Whereas if you look at the artifacts like zero concurrence for these particular states, that is because they are using, at least in our opinion, incorrect benchmarks. Okay. Now comes the final question. I have been keep on saying that concurrence cannot distinguish between this state and the state, although they have although they have different entanglement distributions, what is it that can we say from this kind of a construction? Please notice, ours is completely constructive, completely operational, and of course we have demonstrated it only for the 2-qubit state, but I believe it is a matter of detail for the other situations. So how do we reconstruct the state? Can I reconstruct the state? The answer to that is, if your density operator is a projection, of course the state gets reconstructed. There is no question about that at all, because we are characterizing in terms of locally invariant parameters. However, when I have incoherent superpositions of parameters, I am allowed to do independent SU2 transformations in each of the subspaces. Therefore, different entanglement distributions need not correspond to equivalent operators. There is a certain degree of freedom. This is not surprising because my full space is a 15-parameter space, the state space, density operators, and my local transformation is a 6-parameter space, SU2 cross SU2. Therefore, it produces an orbit of 6 dimensions. There are 9 invariants, whereas I am characterizing my entanglement in terms of 7 invariants. So you need a little bit more of additional information. The bad news is you need a little bit more of additional information. The good news is you need only 2 more bits of information, because 7 plus 2, 9. Of course, if you don't have discrete ambiguities and things like that, what you can actually do, I think I have to go back to my previous slide. So you need to specify another 2 parameters. So you see, this description almost allows us to reconstruct the state and give you a complete information of the entanglement. So, okay, what is the outlook and what is the conclusion? We have a comprehensive description of what entanglement is, but obviously much needs to be remained, because the importance of entanglement to people in quantum information theory is to use it as a resource. Teleportation, implementation of algorithms, so on and so forth. And for a physicist, we are not just interested in qubits, we are interested in qubits, spin 3/2 or spin 1. Eventually one should be able, after all there are NMR systems with spin 1, lithium 6 or whatever. So we would like to generalize it to the higher spins. That is one interesting thing. And if one can do a lot of nice quantum computation with pseudo projection, pseudo spin pure states, maybe one can do quantum computation with pseudo projection operators, identity plus a 2-dimensional projection operator. If one can do that, maybe the cost, in terms of real cost, I mean, maybe less than what one has to do with quantum pseudo pure states. That is another interesting thing. Now, we have said that concurrence and negativity appear as benchmarks, but we have not been able to completely characterize and understand the physical significance and features of our own parameterization. It is like going back to our thermodynamic description. First you say, oh, everything can be understood in terms of temperature. Then somebody comes and says, no, no, you have to give me one more parameter, because it depends on the kind of ensemble that I am looking at. Maybe it is a canonical ensemble, micro-canonical ensemble. I may need some chemical potentials. So the parameters that we are giving are probably of that nature. Depending on the nature, you have to give more and more parameters. We would like to understand their physical significance and understand their role in actually giving us entanglement as a resource for all quantum information theory. And then there is this interesting question of multi-qubit entanglement. I don't look at 2 qubits, but I look at 3, 4, etc., etc. And people have derived large number of results for multi-qubit entanglement in terms of the lower qubit entanglements, and they have all employed benchmarks. But it is a good question to ask ourselves what those results will be and in what way they can get generalized if I were to look at in terms of the distribution functions of this kind. So thank you very much for your attention. I rest my case here.